Hi, very good morning. I think I'm doing this, redoing this tutorial too because I think we found out that one of the students alerted me on some of the mistakes, and that's why I'm actually doing a revised version of tutorial 2. Okay, so we are doing a revised version of tutorial 2. Actually, the mistake is just on the hexadecimal table, but I'm actually attaching the table so that all of us can refer. Okay, so I think as we discussed in the lectures, the status register, okay, we consist of 2 bytes, okay, the upper byte and the lower byte. And this is something that we are concerned with, the N, Z, C, and V bits, or what we call flags. The reason why we call it flags is because it's actually an analogy of people using flags to indicate something. Okay, as you can see, in a war, if you want to surrender, you put up a white flag. All right, and in the airport, okay, flags actually represent a lot of things. Whether you rise the flag or you do not rise the flag, it means two different things. So since most of these flagging states are actually binary, so that's why they refer to this scenario as flags. Okay, so whether you call it flag or bits, it doesn't matter. It refers to the same thing. Okay, so overflow, flag, uh, negative flag, zero flag, carry flag, or you can call it bits, however you feel comfortable. And this few other bits in the status register, they are actually used for low power mode control. And GIE is actually a general interrupt enabler. All right, so it helps you to enable or disable certain interrupt procedures. Sometimes you might not want to have an interrupt, okay, like for example, pin interrupt, GPIO interrupt, and so on and so forth. Now, the easiest way to disable all these interrupts and is by disabling this flag or this bit to 0. Okay, so normally 1 represents set and 0 represents reset in our microcomputer lingo. Okay, so as you can see, there's a lot of reserve bits here. We are not going to discuss at this very moment what are these reserve bits. We're just going to focus on these few bits that are actually important to us. Okay, so the topic of discussion which we are interested is actually today, it's actually in this few flags, okay? We call it a flag or a bit, okay? So these flags actually are important. The programmers can actually check the status of these flags and determine something about the calculation that they have done, okay? So when you've done some calculation in the ALU, you want to check certain answers. It depends on whether you are actually working on an unsigned integer or signed integer. Okay, it doesn't matter, but whichever you choose to mode that you choose to use, whether it's unsigned and or signed, you need to actually refer back to this flags. All right, flags. So in order for you to make sense of whatever calculation that you're doing. Okay, so we're going to do 3 things today. We're going to start off with converting signed to unsigned. We're going to start with converting unsigned to signed, and I mean converting the hexadecimal to either signed or unsigned. Okay, so and then after that, subsequently we're going to move to subtraction and addition followed by subtraction. What happens in this process, that causes the flags to actually change, and we can actually observe, we can actually do a calculation, and we can refer back to the flags. All right. So we take four data, four bytes in consideration for our study for the first section. All right. To convert the hex into either signed or unsigned integer value. In machine language, everything is just binary, all right? Whether it's it's a character, whether it's an integer, whether it's a decimal number or precision number, whatever that you have, it's basically represented in binary. So the same hex that you have can be used to represent signed or unsigned. It depends on the what you want to be referring to. Let me double check. Okay, fine. Still recording. Okay. This is the table that actually I made a mistake in the last previous lecture tutorial number 2. So this is the how you convert the equivalent of a number. Number means integer, okay, to the binary equivalent, and the hex equivalent. If you can see, 0 to 9 is the same, but after 10 in integer is represented by A, B, C, D, E, and F. Okay, so this is hex, all right, and the binary are all the same. That's why a single binary can be used to represent number, hexadecimal, signed number or unsigned number, or signed integer, unsigned integer. All right. Now let's look at this. 9A, it's 1001, 1010. Okay. Reflect back on 9, 1001, and 1010. So this is 9A. All right. So that's how we get the 9A. And if you lay out the binary, okay, I've written it in red color. You multiply for the signed case and the unsigned case is just the most significant bit that you multiply. Okay, so for case unsigned, it's 1 to 8, and case signed is negative 1 to 8. Okay, so this is the negative. If this most significant bit is 1, most probably the whole number is going to be negative. If this most significant bit is 0, most probably, actually not most probably, definitely, all right, you get a positive number. Okay, so this is the case for unsigned. All right, unsigned is just the most significant bit you multiply by 1 to 8. That's why the range will be different. All right. Okay, we look back. B6. So this is the code for B, and this is 6. Similarly, we put the binary bits out. Okay, and we do the multiplication with the decimal numbers. We will be able to get negative 58, and this is 198. Right. So DA is the same. We put it out together. We convert this hex into binary, and then we lay it out together. We will be able to get negative 38 and 218. You just have to look at the most significant bit for case sign. You will definitely know that this is a negative number. When you see the first one becomes 1, definitely the most significant bit become 1, you will definitely get a negative number. So for case of unsigned, everything is positive. Okay. And which brings us to the question, for case signed and unsigned, what is the maximum, the range, the upper range and the lower range that we are talking about? Okay, so for unsigned, we know that the upper range will be 1, 1, 1, 1 and 0, 0, 0. Okay, so the lower range will become 0, and the upper range will become 2, 5, 5. Okay, so there's 2, 5, 6 states because it's 0 index. All right. So, but the case for sign, the upper range will be 0, 1, 1, 1, 1, 1, and the lower range will be 1, 0, 0, 0, 0. Okay, so we can look at the logic of this. The first, if we all these are positive values, and the most significant bit represents the negative values. So that's why if we have 1, 0, 0, 0, that would mean negative 1 to 8. and 0, 1, 1, 1, 1, 1 will be representing 1 to 8. That's the upper range, and that's lower range. So I hope that from this we can actually understand. Okay, you can reflect back previous slide to find out actually how did we get this. But to summarize, signed and unsigned, you have different range. Right. Now, second section, we're going to discuss about the addition operation. Okay. So we have 4A and 79, and this is what we get. Now, how do we get this answer? If some of you are still confused, you do an OR. Okay, 0 and 1, it's 1. 1, 0 is 1. 0, 0 is of course 0. 1 and 1, you get 0, and then you carry forward to the next bit. You get 1 and 1 is also 0. And then you have 1 and 1 is also 0. You have 1. Okay, here 1, and you carry forward, it becomes 1. There's no carry value. Now I'm going to explain to you how do we get these flags. How does this flags operate to become either 1 or 0? Okay. Now have a look at there is the original answer is 8 bits. Okay, but you get a 9th bit because of the carry. Now very important. Look at the carry bit. If this carry bit becomes 1, you will get this as 1. This flag will rise up to be set. Else, this will be in a reset state. Okay. So since the 9th bit, the carry bit, okay, that you carry forward, it's a 0. So you get a 0. Now this negative actually is depending on the 8 bit, the most significant bit in the original byte size. Okay. So since this most significant bit it's 1, so this negative flag you get 1. Okay, so reflect back just now for signed integers. Okay, we always look at the most significant bit to determine whether this answer is a negative answer or a positive answer. So that's why we call it a negative flag. Now what about 0? 0 only happens when you have this section of the answer becomes total 0. So you have 8 zeros, this one will become a 0 flag. Okay, this doesn't depend on the carry. Okay, so you have all this becomes 0, you will get a 0 flag become set. So in this case, this is not 0, this is not 8 zeros, so you get 0 here. Flag will reset. Okay, now this overflow happens when the most significant bit of the original values are the same. Okay, so since this is the same, both are 0, you will get 1. If both are 1 and 1, you get 1. So, but if either of these is 0 or 1, you will get a 0. In this case, both 4A 79 most significant bit is 0, so you will get a 1. Okay, same thing. B4 4C, right? Now, you guys are wondering why this hex? This 4C hex plus B4 hex. Sometimes you have numbers which are integers. Let's say, for example, 1 1. 1 1. If you do not put this hex, it could be challenging for the reader because they might think that 1 1 is 11 in integer, or it could be in hexadecimal in our case. Okay, so that's why this H is actually important to indicate whether this is a hex or a integer. Okay, so even in this case, sometimes they put B at the end of the binary string to indicate that this is actually not an integer, because 0 1 0 0 1 0 0 0 can also be an integer. Okay, you look at that, it can also be an integer. So that's why sometimes they put the suffix here B to indicate that, hey, this is not a integer or a hex. Okay. Now B4 4C, you do the operation, the OR operation, you get 1 0 0 0. Now in this case you have zeros, so 0 flag will become set. V 1 and 0. It's not the same, so you get 0. Negative is 0. Okay, because the most significant bit of the answer, it's 0. And a carry, it's actually 1, because after you have a carry forward, you get a 1. Similarly, 9A, B6, you do an OR operation. Now, you perform, you get this, okay? Now, we're just going to jump straight into how we get this flags. V, 1 and 1, you get V. 0, none of these 8 bits constitute 0 hex, so get 0. Negative, most significant bit is 0, okay? And the carry is 1, because if this is 0, then the carry flag will also be reset, okay? All right, so I hope you're clear. CA 1B, you get the answer. Okay, look at this flag, 1 0, you get 0. Most significant bit, okay, you get a 1, and the 0, none of these answers give you 0 hex, and C will be equals to 0, because the carry bit 0. Okay. Now that we've actually know we are familiar with the addition. Addition is the most basic one. We're going to move on to subtraction. Okay. So subtraction is very easy. If you have x minus y, all you need to do is x plus the 2's complement of y. Okay. So I'm going to leave you guys with reflect back how you do your 2's complement in your foundation digital design. Okay, so it's let's assume that we have this 4 bytes. Okay, we can convert a subtraction into addition by using a 2's complement. Now this is the 2's complement value when we convert from the original value, the 2's complement for x, y, w, and z. Okay. Now let's take this w minus y, you get w plus the 2's complement of y, you get 3c plus 8c. The answer is C8. You get this answer. Okay, now let's look at the flags will flag up according to the addition operation that we've just discussed in the previous section. Okay, so if you don't believe me, let's check out C. Okay, no value. Okay, so it becomes 0. V overflow 0 and 1 0. Most significant bit is 1. You get 1. The answer is not equals to 0 0, so you get a reset for 0 flag. Y minus w equals to y plus the 2's complement of w. You get 74 plus 5e equals to d2. Okay, so this is not d2. I think it's a mistake. This is okay, so this is not d2. Yep, D is correct. 2 is correct. Okay, so it's not D2. Okay, I think this is the one that my previous mistake. All right, so it's a C4 plus 5e. You get this answer, and the carry 0. 0. None of these constitutes. The answer does not equal to 0 0. So the 0 flag will be reset, and the V will be equals to 0 0. It's the same. So you have overflow to be set, and negative, you have most significant bit is equals to 1. So the same. Yep, I think these answers I got it from the textbook. So let me check why I just copied and paste from textbook. I think that could be the reason why. But let me double check the answers from textbook. They could be wrong. Okay. W minus Z equals to W plus the 2's complement of Z. So you have A2 plus 77. You get this answer. This actually just means that there's a carry bit. Okay. So this is carry bit 1. So you have 0, 0, 0. Okay. So it doesn't matter. So carry will be equals to 1 because this is carry. 0 will be equals to, none of these answers equals to 0, 0 hex. Okay. V, you have 0 and 1. So you get 0. And you get a 0. Okay. Similarly, Z minus X, you get Z plus 2's complement of X. You get 1 for D. Okay. So this is 1, 4, and D. All right. Okay, so this is not D. This could be a C. Let me check. 1, 1, 0. Okay, this is C. All right. So you have 14C. So this is 1, 4, and this is C. Okay, because 1100 is C. So let me recheck. I've practically copied and pasted from the textbook, but if you calculate it, you get this answer. C, this is carry. Z, this is 0. Okay, so this most significant bit is 0. So this is a reset. V will be equals to 1 and 1. You get a 1, and N negative will be equals to the most significant bit of the original line. 8 bits, you get 0 because most significant bit here is 0. Okay, so wait, 1100. Let us double check whether this 1100 it's C or D. All right, we refer back 1100 to the original table. So 1100 is indeed C. So I think I will need to recheck why the mistake actually in the textbook. But it doesn't matter, that's not our concern. Our concern is just to be able to do things right. So I hope that you get the answer. So whenever you do a subtraction, Z minus X, you get a Z plus the 2's complement of the whatever that you want to subtract. So this is how you actually do a subtraction. So subtraction, it becomes subtraction becomes an addition. It's much easier to perform. You just do the OR operation, and this is what happened to the flags. So it's very important for you to know what happened to the flags and to be able to estimate. Okay, I give you two values. You do an addition or subtraction. Or what are the values of the flag after this operation? You should be able to tell. Okay, so that's all for today. Hope that you've benefited. Again, these tutorials are a revision of the previous one. I'll delete the previous one because of some errors. Okay, thanks.